This is the screencast for section 4.4, example 1. We're going to look at the graphs of sine and cosine functions, as well as sinusoids. Now hang on a second, I'll tell you what a sinusoid is. It is not an extinct animal. The sine function, basic characteristics are right here, along with a graph, and we'll explore that in more detail later. The cosine function is right here. Again, we're going to explore that in more detail later. The next page of your notes defines what a sinusoid is. A function is a sinusoid if it can be written in the form a basic sine function with a horizontal stretch or shrink, a horizontal shift, a vertical stretch or shrink, and a vertical shift. So a sinusoid is a version of the sine function just with some transformations. Now, looking at a specific characteristic of a sinusoid, the amplitude of the sinusoid, which f of x equals a times sine of bx plus c plus d, is half the height of the wave. So your book says that that's the absolute value of a, and I'll show you why in just a second. So we're going to find the amplitude of each function and use the language of transformations to describe how the graphs are related. So we're going to in y1 graph the cosine of x, and then b in y2 we're going to graph 1/2 the cosine of x, and then in c y3 we're going to graph the opposite of 3 times cosine of x. So now I've got all three graphs put into my y equals, but I'm only going to turn on y1 for right now, the cosine of x. I'm going to look at part A first. My window, now I've got a lot of options here. My x-axis, what you're going to plug into a cosine function is all the angles in radians. We're going to definitely be in radian mode. Now I want to look at this angle maybe from -2 pi to 2 pi. That might change from problem to problem, but -2 pi to 2 pi is a pretty standard window for trigonometry. Now my x scale, going by ones doesn't really help me any because I'm scaling this by 2 pi. So instead I'm going to change to pi over 2 for my x scale. So I'm going to get all my quadrantal angles marked on the x-axis. Now my y min and y max, I think -5 and 5 will be okay for this problem. So here's the cosine of x. The number out in front, a, is technically 1, and your book is right, but I want you to understand what that means. The cosine of x, half the height of the wave, is called the amplitude. Well, this wave stretches from -1 to +1, which is technically a height of 2, but half the height here is 1 unit. So the amplitude is 1. Now, if we look at y2 and graph, let's leave cosine of x on, but we'll add 1/2 cosine x into that graph. We have, as you may have suspected, a vertical shrink by 1/2. So I'm going to use that description, a vertical shrink by 1/2. And now my amplitude goes from -1/2 to +1/2. So my range is only from -1/2 to +1/2 because I shrunk all those y values down by 1/2. So that means my amplitude is, let's see, if it goes from -1/2 to 1/2, the height is technically 1. So the amplitude, half the height of the wave, is 1/2. Now part C, you can already predict that that's going to be a vertical stretch by 3, as well as a vertical flip over the x-axis. So let's see what that one looks like. So now this guy, the height of the wave stretches from -3 all the way up to +3, which is a height of 6, so the amplitude then is going to be half that height, 3. The now try problem number 1 says find the amplitude of the function and use language of transformations to describe how the graph of the function is related to the graph of y equals sine of x. Well, as you can see, this is a vertical stretch by 2 because we're multiplying the outside of the function by 2. which means instead of the range going from -1 to 1 on this sine function, the range is going to go from -2 to +2, which is a span of 4 units. So the height of the wave is going to be 4 units. Half the height of that wave, or the amplitude, is going to be 2. Let's take a look at that. There's the graph. You can see the range goes down from -2 all the way up to +2. Therefore, that is a total span of 4 units, meaning its amplitude is half that.